Okay, so the next major topic in CoCO is combinational circuits synthesis, and we are going to be focusing on logic minimization using Karnaugh maps. That's what we are trying to do here. And this is one of the very crucial topics of the course. This turns out to be a fun topic for many students. It is easy. It is structured, so there is a process to do logic minimization here. So I hope you guys, K-maps are honestly, yes. I feel that too. So let's build some motivation here first for circuit manipulations. So if you are given an algebraic representation of a logic circuit, for example, a Boolean function, then you might want to simplify things. You might want to reduce your cost. You might want to, you might want to replace and or not with more efficient gates like NAND or NOR because they are universal. You can buy just NAND gates or you can just buy NOR gates and you can implement any function that you want because they are universal. So that's more efficient way to synthesize logic functions. You may also want to simplify or minimize the expression. Now, the obvious next question is there a way, is there a metric to know how simple or complex the logic expression is? Now, it turns out for logic expression, there is no one consistent metric to find the cost of implementation. The metric can be different depending on the digital designer. Let me talk about this first. It could be, what is minimization? Okay, so hold on. Okay, so let's talk about the rationale for logic minimization. If you wanted to reduce or simplify or minimize a logic expression, some could say, let me just reduce the number of literals, and that's how I minimize the logic function. Some other digital designer might say, let's just reduce the number of logic gates. Because if you reduce the number of logic gates, you reduce the number of transistors, and that's it. Let's just focus on that. And somebody else might come and say, no, timing is very important to me, so let's reduce the number of levels of gates. So instead of having 5 levels, let's go to 2 levels. And while they are going through these options, they are probably looking at a few things to worry about. So for example, fewer inputs implies faster gates in some technologies. We also saw that fan-in is a limitation that we'll have to deal with while we are going through those rationale for logic minimization. Fewer levels means reduced propagation delay. And minimum delay configuration typically requires more gates, and it actually increases fan-in as well. So these things that are they are actually related, sometimes contradictory to each other, which is why there is no one consistent universal metric for simplification. But there is a way for us to simplify the expressions using Boolean algebra and K-maps, and we'll talk about that. Now, we talked about making things more efficient by using NAND gates or NOR gates. One such example is presented over here. We can go through this quickly because we have seen this in the previous class. On the left, we have a NOT gate, AND gate, and OR gate. So we have a AND or NOT circuit, basic gates. We can manipulate this to get it to a NAND only synthesis. We saw this before, right? Add a bubble, add a bubble. Every time you do it twice. So this cancels out. That has become a NAND gate, that has become a NAND gate, and you can implement this as a NAND gate as well. So it is very easy for us, and you get that, right? So it's very easy for us to manipulate logic diagrams for a NAND only synthesis or for a NOR only synthesis. We can do that very quickly by just adding bubbles 2 at a time and then doing some simplification. And similarly over here, right? So we are trying to convert this to a NOR only synthesis. So if you want to convert this to a NOR only synthesis, output, input, output, input, output, input. That's it. This is a NOR, NOR, NOR. And this is also a NOR. So you've got 4 NOR gates. 2 of them are 2 input. Two of them are 3 input. So there, 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 and there. So the claim is very general. The claim is for any logic function, you can just go to NAND. For any logic function, you can just go to NOR. And you just need to be familiar with how do you push bubbles through. Some of these things that you're exploring in the homework as well. Now let's talk about minimization. Minimization, as the name suggests, is just a process of reducing a complex expression or an equation into a simpler form. Fewer terms, remove redundancies. For example, we just had a duplicate terms situation earlier in the lecture, and we just reduced the redundancy. We just removed the redundant term. So the goal is the function could look very complex. You can simplify it, you can minimize it. But after you minimize, the function should not change. Now, when I say the function should not change, you guys are probably going to think about one thing that uniquely defines a Boolean function. What is that? One thing that uniquely defines a logic function. Truth or dare, truth serum, truth table. Yes, truth table. So the truth table for the function should not change before minimization and after minimization. That's the thing that, you know, that has to be the agreement. Like that we cannot break. Now, minimization, we have done a little bit when we are looking at Boolean algebra simplification. We did that using Boolean algebra properties. But when we did the Boolean algebra properties, I'm sure many of you left with a feeling of maybe I can do this very well at many occasions, but I might have a challenge on my hands when I do this for complex Boolean expressions. And you had that feeling because the nature of Boolean manipulation is such that as the number of variables increase, you may or may not be able to say for sure if you have reached the simplest form or not. So even though you might have done everything correctly, Boolean algebra doesn't give you a very methodical, very structured way to simplify expressions. And one of the drawbacks there is that even if you get a simple answer, it might take you some time to actually be 100% sure that that is the simplest form. Which is why we are talking about K-maps or Karnaugh maps. They are structured, they are methodical, they guarantee you that you will get the simplest expression. So that's what we are going to be doing. Now let's take some measures, some metrics to measure complexity. Over here, as I said earlier, various people use various ways to measure complexity. Here we are using the number of literals to find the complexity. We already defined the literal. Literal is an appearance of a variable in true form or a complemented form in an expression. So if you look at this expression here for z, which depends on inputs a, b, and c, it has 10 literals. It has 3 input variables. It has 10 literals because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 literals. And after you simplify this using either Boolean manipulation or by using K-maps, which you are going to learn, the goal is, do those number of literals go down or not? Hopefully they do. We talked about the logic here. Now let's introduce K-maps. K-maps are essentially a truth table in grid form. That's all it is. A truth table in a grid form. And we already were talking about the motivation for using K-maps. It's a systematic approach to logic expression minimization. And if you follow all the rules exactly as they are laid out, you are guaranteed to get the simplest form of logic expression. Note 1, logic expressions are not unique. Clearly, you have an expression before simplification and after simplification giving you the same truth table. So they are not unique. Note 2, simplest form of the logic expression is also not unique. And while we are doing examples of K-maps, we will see this, how the simplest form of a logic expression is not unique. So those are 2 key notes. Next, a Karnaugh map or a K-map is a grid view of a truth table. The input variables are distributed on the rows of the grid and columns of the grid. The grid can contain 3 entries, 0 for logic 0, 1 for true, X for a don't care situation. Those are for the grid cells. The cell entries evaluate the output variable for that specific row and column. This becomes a lot easier to follow once we look at an example. We are going to have a 2 variable K-map, we are going to have a 3 variable K-map, 4 variable K-map, and we will also do a 5 variable K-map. So 2, 3, 4, 5 is what we will go for. Let's talk about the underlying trick. The trick is to answer the question, what makes K-maps possible? In order to explain that, I would say consider this function f, x and y or x and y complement, and start using Boolean algebra to simplify. Well, clearly x is a term that is common to both the product terms over here. So you can pull that out as a common factor. And once you do, you will be remaining with y or y complement inside the parentheses, which is 1. So you will simply get x at the end. And if you notice the starting point and the ending point, you can make this comment. The variable that changed got eliminated. All of K-maps is based on this simple trick. This is the fundamental trick that we are going to use many times in a very, we are going to leverage this trick a lot for K-maps. The variable that changed got eliminated. Just to test here, we can do this. say f is a and b and c, or a and b and c complement, the variable that changed gets eliminated, right? So what should be the answer here? AB is absolutely right. So you didn't have to go through this process, but just because you recognize the property, you can leverage that to write that answer out. Now I'm going to lay out the rules, but maybe we don't have time to work through many K-maps, but I'll just simply lay out the rules for you guys so that we get a start. The rules to determine the simplest SOP. So first we are going to focus on simplest sum of products expression. The rules are to group adjacent ones in the K-map, and the size of the groups can be 1, 2, 4, 8, 16, or in general powers of 2. For a sum of product expression, you have to cover all the ones in the K-map, which in other words means the groups should be over all the ones in the K-map, not the zeros, but the ones. You should cover all the ones. You should leave out the zeros. A diagonal is not adjacent. Only one variable is allowed to change. Why? Why is only one variable allowed to change? Because of this, right? Only when you have one variable changing, that's the one that gets eliminated. It turns out that when you have a diagonal in a K-map, more than one variable changes at the same time. So you cannot allow diagonal to be adjacent. Another rule, edges wrap around. A grid view with a wraparound edges. The K-map actually wraps around both horizontally as well as vertically. You can combine the 4 corners into one group. This applies for 3 variable K-maps and 4 variable K-maps. And we are going to treat the don't care, which is X, as a 1 only if it helps us make a larger group. Otherwise, we are going to treat that as a 0. So all these rules, I'm just saying that right now. And for those of you who want to take a look at the slides that are posted on Piazza and start making connections, you are welcome to do that. But we are going to actually apply these rules to many, many examples for K-maps in the next lecture. So that's when everything will fall into place. Now, the rules are very similar when you talk about the simplest product of some expression. The only changes are, instead of grouping the ones, now you are grouping the zeros. Instead of covering all the ones, you are covering all the zeros. And you are going to treat the don't care as a 0 only if it helps you make a larger group. Otherwise, we are going to treat that as a 1. So only at those places you have, this also changed to zeros. So the rules are more or less the same. The main difference is we are going to be combining the zeros in a product of some to get the simplest POS expression. Now, while we are doing K-maps, we have an overarching goal. The goal for K-map simplification is, as you are making these groups, you want to make the largest possible groups of adjacent ones. You can reuse cells in a group in order to make larger groups. How many number of groups? Well, you make the fewest number of groups, because fewest number of groups means fewest number of terms. The bigger the group of adjacent ones, the smaller the resulting term for that group. All right, so those are rules and the goals for K-map simplification. let me just do one example and then we'll stop here. So this is a two variable K-map. I have X and Y as my two inputs. I have F as my output. Now, can you guys, maybe think of an arbitrary sequence of zeros and ones? Give me 4 bits. It could be a 0, could be a 1. 4 bits. 0, 1. Okay, so 0, 1, 1, 0 is the first one that I got. So I will take all of zeros. Okay, so all ones and all zeros will be F is 0, F is 1. So let's use the first one, 0, 1, 1, 0. All right, so I've got 0, 1, 1, 0 here. So I'm using that. Next, what did we do here? We took a truth table and we put it as a grid. And on the columns, we have X distributed on the columns. X could be a 0, could be a 1. So X is distributed, the input X is distributed on the columns. And input Y is distributed on the rows. Now let's go from the truth table to the K-map. Where are the zeros? So where should I put the first 0 here? So I should put this guy right here, because that's when X is 0 and Y is 0. I should put this guy over here, because that's when X is 0 and Y is 1. I should put this guy over here, because that's when X is 1 and Y is 0. And of course the last one. That's how you go from a truth table to a K-map. Then I'm going to simply erase this because it's causing a distraction. Now, this turned out to be we cannot do any groups here because diagonal is not a group, right? This is a diagonal. So I cannot make a group there. So I'm going to change this to a 1, which means I'm going to change this to a 1 so that I can make some groups. The groups are going to be as big as possible. So my first question will be, can I make a group of 4? Can I make a group of 4 ones? I can't, because there is a 0 there. So I cannot make a group of 4 ones over here. So the next best thing I can do is, can I make a group of 2 ones? That's the next best thing. And the answer is yes. Yes, twice. You got it. So let me just highlight those groups. One would be right here. And the other would be right there. Two groups of adjacent ones. Now, that's it. Now I just need to write the product terms for each of these groups. So for this guy, for the vertical group, what is X? X is 1. What is Y? Now X is 1. What is Y? For the vertical group. 0 or 1. Exactly. So when it is 0 and it is also 1, that is the variable that is changing. So if it is the variable that is changing, it gets eliminated. So for the vertical group here, you simply get X because it is a 1 there. Y is changing, it gets eliminated. Now let's take a look at this guy. For the horizontal group of 2 ones, Y is 1 and x changes. So x gets eliminated and you get y. That's it. So the simplest expression here would be x or y. We are doing this for simplest SOP. Notice we reused a cell to make larger groups. So we followed all the rules and we got the simplest form. Now, if we did not have this strategy, what would we write? We would write f as x complement and y, or x and y complement, or x and y. And then we would try to simplify this by maybe taking something common, maybe duplicating terms, and then we would use essentially Boolean algebra properties to solve this. The same thing we did using K-maps. It took a few minutes. All we had to do was ask the right questions in the right order. And you started with the first question as, can I make a group of 4 ones? The answer was no. So you asked the next highest, can I make a group of 2 ones? And then you made those groups and you identified the product terms. Product term, and then SO products. So that's essentially how you will go about doing this. Next lecture, we will have a lot of fun with many examples. We will go to a 3-variable K-map. We will go for a 4-variable K-map. We will also go for a 5-variable K-map. So this is going to become very interesting. But the best is it is structured, and all you have to do is follow the rules. All right, let's stop over here, guys, and then pick it up on Friday.